magnetic skyrmions. Okay, Axel, the floor is yours.
Alright, so, so first of all, thank you all for actually listening to my talk and for the organizers to invite me, getting my chili fix. So I mean, you spent sufficient time in Los Alamos, I'm still addicted to this. Oh, this is fun. Yes. Okay, so here's what I will tell you. By popular demand, I have to show you this image and the movie's relation to that. But I'll keep that brief and try to show you some things that maybe not all of you have seen yet. There we go. So here's essentially what I want to show you. I'll show you one slide on Skyrmions and multi-layers because in this audience I don't have to motivate things too much. I'll talk briefly about what we have done in glowing Skyrmions. I'll talk about Skyrmion artifacts, and then I'll talk about different multi-layers where you can get smaller Skyrmions and when you're familiar with them all. There we go. Skyrmions. So you all know this by now. Magnetic skyrmions distinguish themselves by having being a spin texture with a non-trivial topology. You can express this in terms of topology of charge. If you express it like this, one thing that I would like to point out is, as you can see, this quantity here is odd in magnetization. So if you reverse the magnetization, you actually change the sign. You'll see how that is important later. You can get skyrmions via chiral exchange interactions. You don't have to have that, as what Eric showed, for example, and many others. But it helps if you have them. You can have them due to bulk inversion symmetry breaking, or you can have them due to inversion symmetry breaking and interfaces and multi-layers. So some of the reasons why people get excited about it is because having a topological charge actually gives rise to some additional physics, like emerging magnetic fields that can be relatively large for small skyrmions. That gives rise to topological Hall effects and also maybe a different angle on how you can interact with skyrmions. But what's also interesting in terms of these multi-layers is that you can move them by using transverse spin transfer properties such as spin Hall effects or spin orbitals in general. And it gives a very efficient way of moving them. So, putting this all together, I'll first briefly recap one of the things that we've done now a couple of years ago about generating magnetic skyrmion in a mechanism that many of you are very familiar from childhood, like blowing soap bubbles. It's essentially the same kind of Welling-Taylor instabilities that you see in surface tension with fluid flows. To do this, we start off with the following sample structure where we take the cobalt iron bond film, which we sandwich between tantalum and tantalum oxide. Why do we use these two layers? Tantalum oxide, by having oxygen at this interface, generates a perpendicular anisotropy. And the tantalum is well known for giving large spin orbitals, which then very efficiently can manipulate the magnetic structures in the cobalt iron bond. Now, also by having two different layers on top and the bottom, we have a net Jarzynski-Mounier interaction that gives a net chirality to the spin structure that we see. So first, this is just magnetization with the field of these layers. You see it's indeed perpendicular anisotropy. The blue data points are measured with the field perpendicular, the red with the field in the plane. The perpendicular anisotropy is rather small, so we're very close to a spin reorientation condition, similar to the talks we heard earlier this morning about experimentally and theoretically. Now, it's also well known that you have these materials with perpendicular anisotropy, and you look at the magnetic domain structures, let's say, with Maneiko optic hair effects, you get these stripy labyrinth type of domain patterns. If you now bias the system in one direction, you bias it towards the white domains here. Or if you go in the opposite direction, you go to this dark domain. So what we have done then is we take one of these films, we pattern it into a wire. Here it's like 60 micrometers wide. Here the construction is 3 micrometers wide. We apply a small magnetic field that gets us into this stripy phase where we have mostly single stripes of one type. And then we apply current that pushes this domain structure through this constriction, and when this band domain emerges out on the side, it actually breaks up into individual bubbles, which you can see here. So you generate all these individual bubbles, which have all these spin texture. Now, a couple of things when you look at this, if we notice, is there's an apparent repulsive interaction between the bubbles. We don't really see bubbles merging in these films. If you look very careful, you see some preference of the bubbles moving towards this quadrant of the film, and then I'll get back to that in the end as well. So, what we think what is going on here is schematically like this. We know from work that Jeff Beach, for example, did at MIT, and Stuart Parkin's group at IBM, that if you have these magnetic films where you have chiral magnetic domain walls, then the spin-orbital is very efficient at moving these chiral domain walls in one specific direction. And this happens if you have pilot this film into a narrow wire where the domain wall goes across the whole width of the wire. Now, what happens if you put this band domain in a more extended film? Well, it turns out, if you look carefully, the spin-orbital is most efficient when the current direction is collinear with the magnetization in this domain wall. So that means as you pass the current through here, you get strong spin-orbitals here, so it moves the tip of this part domain. There are no spin-orbitals on the sidewalls, so they are totally unaffected. So in essence, you can just take this part domain and allocate it. Now, once you put such a spike domain in this constriction, things change a little bit. Namely, what happens is now the current flow is not homogeneous anymore. You get an inhomogeneous current. So now you not only have current in this direction, but also in the side direction, which then generates an additional force on the side walls of these band domains. So it starts to expand it, kind of like blowing up the soap bubble. And then you get surface tension takes over, you get the netting instability, and you rip up an individual bubble, very much like this really instability. And this you can do repeatedly, so you get as many skyrmions as you want out of a single band. Very much like what we saw. Now, I think this is in general a very interesting concept that you can use inhomogeneities to generate skyrmions out of nothing if you want so. In this case, it's an homogeneous current distribution, but you can also start with an inhomogeneous magnetization distribution that I think will be shown by Karen and also by Jeff, maybe, I don't know for a second. But I know he does things like that. So it's a much more general phenomenon, I think, than what I'm talking about here now. So, of course, this was just a simple schematic hand-wavingly that we came up with. We wanted to see if we can see this in actual electromagnetic simulations. And we wanted to see it for parameters that are similar to the parameters that we expect from our fields, which is a problem because the magnetic domain structures in our fields are very large, so we make electromagnetic simulations with the same parameters that we expect from our samples. The domain patterns are also large, and the simulation becomes very expensive. So we made it slightly smaller here. Instead of 3 micrometers, this is just a few hundred nanometers, so you can't fit the whole band domain. We just have the end of the band domain here. And then what we do is we apply the current pulse for 30 nanoseconds. What you will see is that this domain wall starts moving. You will see that it moves a little faster on this side than on this side. This is a consequence of the DMI actually. And then eventually there will be an instability. It happens when this hits this corner, but it's actually unrelated to it. We have other simulations where it happens all the time. And then things are very complicated. We switch off the current, you see this domain wall retracting, but there are some individual skyrmions left in the end. So here you see this move now becomes complicated and very messy. You see various different bubbles created and going away, but then eventually now the current is up, this reflects. So we have individual skyrmions here, that are left over. Note that they're in this very high energetic state where they're deformed, and as a matter of this deformation, they continuously rotate around itself, which is interesting in itself. In fact, it was kind of curious because if you look at this micromoonade simulation, these dynamics is very long, much longer than what we typically see in micromoonade simulation. But there are good reasons for that too, actually. So, but then we said, okay, let's just crank up the current and see what happens. If we now take a current that's like 10 times bigger, then while we apply the current, there's no well-defined domain law structure left in the sample anymore. Now, the phenomenon disrupt the domain structure so much that you pull the magnetization mostly in plane everywhere. And but if you switch off the current now, then you see the system relaxing again into individual bubbles that have this very long-lived dynamics. Some vanish at the edge, but it's another way of how to create skyrmions out of nothing. It's interesting because this is a distinctively different mechanism than the one that I showed you before. The one before, we take essentially an existing domain structure and then just modify it a little bit and rip off the new domain from the existing one. Here we create new domains out of violently disturbing the system out of nothing. So we thought, oh, this is interesting. So can we do this actually experimentally? And the answer is yes. So we can take the same samples as before. But now get rid of the bridge in between and replace it with just a small conducting bridge made out of titanium gold. So it's very highly conducting, so there's not much heat generated. So there's no magnetic structure transfer from one side to the other. It's just an homogeneity of the current that is here. Now, we expect from the simulation that this requires larger currents. So the movies that I'm going to show you, instead of using a DC current, it will have pulse currents. But here you see the sample. And now as we pulse the currents at 1 Hertz, you see that with each current pulse, we do generate new skyrmions here. Pretty much out of nothing. There's no pre-existing magnetic structure that sees this. So it's only this homogeneity of the current. So now that we have studied in detail how to generate these skyrmions in these kind of structures, we wanted to see if we can look at something else. And something else that we were interested in is the skyrmion Hall. Now, many of you are, I'm sure, familiar with the conventional classical Hall effect, which is if you take an electric charge particle and move in the presence of a magnetic field, it gets deflected sideways due to a Lorentz force acting on it. And so we use this to see what kind of carriers you have in your samples that getting carrier densities and so on. It turns out, for skyrmions, you expect something similar, and this picture is where if you have a skyrmion and you put a force on it, it also likes to move sideways. And the reason for that is because you have this underlying gyrotropic dynamics of the magnetic structure. So the deflection that you get is now related to what's known as a Magnus force. You see it looks very similar here, and you get very similar behavior. So the Magnus force is something that's very well known from rotating objects as they move through the air, carrying like soccer balls, but here, maybe like baseballs or golf balls or whatever your favorite pastime is. You do see this if you do a micromagnetic simulation. Let's say you make a slab of a material, put a skyrmion in the middle, you drive it with an electric force, you see the skyrmion moving initially sideways until it gets close to the edge where it's repelled, at which point it starts moving parallel to the applied current. You can also analyze this more carefully by taking the LANL-SkyrmionWorkshop equation, assume you have a rigid skyrmion, and transform it in what's known as a Thiele equation, where you have these three terms. One is the driving term, which determines the force acting on the skyrmion as a function of the current. In the case of if we add skyrmions and spin-orbitals, this force is actually aligned with the current. Then we have a dissipative term, which contains the magnetic damping constant, and also another constant that relates to the size of the structure. And then you have this third term, which is this gyrotropic force here, this Leibniz force, which is directly proportional to the topological charge of your object. So, by analyzing this formula, you can actually determine the initial direction of the motion, or the direction of the motion if there are no boundaries interfering in any way. And so the ratio of the transverse longitudinal velocity is just given by 1 over this constant. So alpha is the magnetization damping, let's say of the order of 10 to the minus 2. D for very small skyrmions is of the order of 1. So meaning this number is rather small, so the motion is mostly in the transverse direction. Can we see this? Well, in the samples that I've shown before, the current distribution was very inhomogeneous, so it's hard to do something quantitative. So here what we do is we take a wide wire where we have mostly, where we have a pretty homogeneous current flow. We have skyrmions created a little bit outside up here. And then what you see is that these skyrmions indeed all move at a well-defined angle, pretty much following this direction indicated. And now if you look in more careful at this, as I said, when you reverse the magnetization by reversing the magnetic field, you also reverse the topological charge, and you expect the sideways motion being in the opposite direction. And indeed, that's what we see. Here is a measurement with positive magnetic field, here is one with negative magnetic field, and indeed here it moves downwards, there it moves upwards. We can look a little closer. These images are taken with current pulses. So essentially the images that you see is before and after each pulse. That's why the motion is so not smooth. But if you look at the displacement in x and y direction after each current pulse, we do see that at these current densities, we are very close to the flow regime where the motion is really very reproducible, both in x and y direction. Now, if we reduce the current significantly, here by a factor of 2 essentially, we see something slightly different. Now, the motion is actually mostly in the direction of the current, but you also see that the motion is much more stochastic, indicating that we're really in the creep regime for these structures. So if I do the same thing, you see that both in x and y, the displacement is very violent, and it's really mostly driven by the spinning landscape in this structure. We can analyze this more quantitatively by looking at the current dependence of this skyrmion Hall angle. We see here, this is for positive current and positive magnetic fields. This is for positive current and negative magnetic fields. And these two are for negative currents. And this is positive field, negative. So just focus on the top quadrant here for a moment. At low currents, we see that the motion is essentially along the current direction. And then at some critical current, we see the onset of this transverse motion. And then gradually, the linear fraction increases until we reach at a higher current regime where the angle just simply saturates, indicating that we are fully in the flow regime of the skyrmion. So at this point, we would expect that the angle is very well described by this Thiele equation, because at that point, the pinning in the sample really shouldn't matter that much for the motion anymore. Now we can calculate what to expect. Now, in a simple model, this constant d is directly related to the diameter. Gamma GW is like the size of the domain ball, which in our case is like 10, 20 nanometers, something like that. If we take our good best estimates for what alpha and d should be, we get an angle that we expect of about 40 degrees, and experimentally we measure something around 30 degrees, so that's reasonable. What's more interesting is, from this you also expect that the skyrmion Hall angle should increase as you decrease the size of the skyrmion. Now, we can play a little bit with the field. If we go from 4.8 to 5.4 Earth, then we decrease the skyrmion size from about 1,000 nanometers to about 600 nanometers, sorry, from 800 to about 600 nanometers. And indeed, we see that the sector time goes up very much consistently with what we expect from here. Now, even better, we can compare this also to numerical simulations that were not done too far from here in Los Alamos, by Charles and Cynthia. I think both were in the room. I see Charles. There. No? So they made numerical simulations treating the skyrmions as point-like particles with this additional alignment fault. And indeed, they see that when the driving force is below the pinning force, you have a reduced skyrmion Hall angle that gradually increases. And then in such a way, it's very similar to what we see in our experiments. And I think Charles is going to talk more about this. Now, since many of you have heard all of this before, I figured I have to talk about a few things you haven't seen yet, unless you heard me at my last conference. So, Jeff, you have heard it. So, one of the nice things about these magnetic multilayers is you have lots of degrees of freedom that you can play with to manipulate the size and other things of the skyrmion. You have interfacial interactions, you have anisotropies, you can also change spin orbit torques at different angles. So there's lots of room for improving various things depending on what you do. And so in particular, it allows you to go to smaller skyrmions. So one way that has been very promising pursued by various groups is to start with platinum cobalt, because we know that it's perpendicular anisotropy, which we like, and then add just another third stereo. Eric used osmium, we used other things that I'll show you more. And then you take this vertical layer stack and you continue it over and over. So I'm going to show you results with manganese, tungsten, iridium, and gold. Structurally, these samples look okay. You get low angle X-ray reflectivities, which Eric knows how to interpret. So I'm sure you can say this is okay. And you have perpendicular anisotropy and so on. So one thing that we can do then, for example, here is various multilayers with iridium, where we change the number of repetitions. At low repetitions, the skyrmions are large enough that we can still see them remote. At higher repetitions, they become smaller, so that we look at them with long TI. And we see that the size goes down continuously, and kind of saturates at some point after Now we can look at the various different elements that we have used: manganese, tungsten, iridium, and gold. These are all images taken in resonance in zero field. And in all of these, you do see skyrmions, which isn't necessarily a good thing, because it probably means that we have enough defects that the system doesn't relax nicely. And also, if you want to do dynamics of it, you will see it doesn't behave all that well. But you see, with manganese, actually, you get mostly a striking pattern, which means you don't have as many defects as with the others. And the structure is actually very small, which I think makes some sense. Listening to Stefan talks about so many times. But gold seems to be a very good sample. Tungsten gives you rather large skyrmions, iridium somewhere. So one thing that we can do is we can look at how the size evolves as a function of field. So we know, we apply fields, we squeeze them and make them smaller. So here you see now there's not CM imaging. As you see, as we increase the field, they become smaller and eventually they vanish. If you look carefully at it, you see that the size evolves like this, and at a critical size, they all vanish independent of where they started. Which again, I think shows you that there is lots of variation with fitting in this sample. One thing, if you want to compare to theory, is that at first sight, this doesn't look very good, because if you look at the theory, what you expect is much of the field, you see that the size should increase quickly and then slowly, or we see exactly the opposite behavior. which again, I think, just indicates that the structures get trapped in metastable position. But if you look a little bit more careful, if you look at the energy of the skyrmion as a function of size, you see that the minimum here is actually fairly shallow. So it's very easy to imagine that the pinning keeps the sizes bigger than you want to actually decrease the magnetic field. And in fact, you would expect some kind of hysteresis, which other groups also have a similar sample. Nevertheless, you can now make a good educated guess what the DMI should be. And here, in Axel's case, you get a DMI of about 1.5. So which is a little smaller than what you get, let's say, with platinum cobalt iridium. So that actually the tungsten is probably not the best possible material to use. So interestingly, the largest values we get is actually by using gold, where you get the DMI of 1.6. Another question that we were interested in is, do induced moments play any role in any of this? And I think that's important information for some of the theorists who want to understand things. And so we did some X-ray circular dichroism. Here for the samples of iridium, here with the samples of gold. We see in both cases actually a small magnetic moment. We can quantify it for the iridium. There we have put enough data to apply some rules. We get a spin moment of 1.02 for microns, an optical moment that's not of magnitude smaller. Now for the gold, unfortunately, one of the absorption edges coincides with one of the other absorption edges of one of the other elements, so we cannot do this analysis quite as nicely to get quantitative numbers. But anyway, what I hope this all shows to you that you can get skyrmions in lots of ways, lots of nuclei. You can have lots of fun with it with skyrmions in complicated projects like this. And you put currents through it and move down, up, around. So have your own fun with skyrmions and knock yourself out. But I'm preaching to the choir here anyway. So this is the group that made all of this possible at Argonne. Most importantly, this guy, Wan Chun-jan, he was really the guy that started and wrote our skyrmion work, and he moved last year to Tsinghua University. If you prefer names instead of places, here are all the various names. Wan Chun, as I said, is the main writing force. A couple other postdocs that were involved, the visiting students. Ola Heinonen did the microtech simulations. That showed Susanne Felder was really my partner in crime in this, where she wrote in about the whole imaging. Amanda Fett along with the people at the LANL-SkyrmionWorkshop. The samples of the cold iron ore between tantalum and tantalum oxide came from UCLA, from the Cameron School. The simulations for the spin Hall effects were done by Lu's group, and by now we have Zhao Wang, who comes from Yu Chang's group in Mar College, doing the work with these nuclear layers that I've shown. So here is the summary of my talk. You can get interfacial magnetic skyrmions using interfacial interactions, and you can summarize them at room temperature. I guess I didn't say that explicitly. Everything I showed you were room temperature measurements. By looking at tantalum, gold iron ore, and tantalum oxide, you see that you can use inhomogeneous currents for generating skyrmions. These don't necessarily have to be inhomogeneous currents, there may be other inhomogeneities that are important. You've seen that the topological charge matters. It gives rise to a well-defined transfer of motion, the Cameron Hall effect. And by looking at various different motor layers, you can definitely get sizes below 100 nanometers, maybe smaller. With that, thank you very much for your attention.
Thank you very much. It was a very nice talk. I was looking for discussion. Yes, I was wondering for the motion, how does the interaction between the X and the
Very good question. I did leave this out because I wanted to have time to talk about different things. But let me see if my computer cooperates. I'll show you. What we see is, what we see is experimentally you expect that the repulsion from the edge should increase the velocity, because you should have that associated with that repulsion. We don't see that. So what we see is that the velocity for the skyrmions that are moving close to the edge is actually reduced. We think that is probably due to the fact that close to the edge we have more defects due to the pattern process. That's our hand-bearing explanation. We do see that the trajectory is very random in a way. We see a random up and down motion after each current pulse, which I think essentially what happens is during the current pulse we push it close to the edge, and then it recoils and gets stuck at some random position away from Sure.
So have you been able to move any of the smaller skyrmions?
Not very well. Not well enough for showing anybody. We had some success moving some of them, but not to where we can get something very conclusive. It is generally
high with that first image there.
Sorry?
You sort of set the bar high with that first image there.
Yeah. So there are certain combinations of materials that I think that are more promising than others. Once I see how it really works, I'll be happy to show you.
You measured also the ball.
Yes.
And then you get about 30 degrees. You can also measure alpha independently. You probably get a different ball. And the difference, do you think, is related to the fact that the damping of skyrmions and the background is different than the Hoffmann state?
Okay, so when we do this comparison here, there's a whole bunch of things. So first of all, you do need to know the damping, which we really don't know, but a typical number would be like 0.02. So the next thing is that in order to get this number very well, we would know the width of our domain model, which we also don't know because we don't have enough resolution to get that number. So we calculate what the width should be based on the exchange interaction and the anisotropy that we know and plug those numbers in. So given all the many things that we don't know so well, I think the agreement is reasonably good. And it just is real big efforts to get those numbers better, to get a better comparison.
You work with the
Thank you.
if you allow me to make one small critical remark.
Absolutely.
There is a detail of the very first paper where you talk about the analogy of the waving instability.
Yeah.
In soap bubbles. I think it doesn't hold up. I think in soap bubbles, you have a two condition rotation point, so the surface area reduces as it reaches up.
Yes.
But in the two-dimensional film, you have a line that tries to reflect and bring the line tension in analogy with the soap bubble. It will tend to straighten and continue the diffusion within the
Yeah.
Obviously, I think the analogy is very
No, you're raising a very interesting point, because when we look at it very, it looks very familiar, like if you have like a garden sprinkler. And so naturally this came to our mind. And we thought at some point maybe we can use these kind of structures to gain more insight into the type of dynamics that we have in these surface tension fluid flows. But in the end, you're absolutely right. First of all, this is 1D versus 2D, 2D versus 3D kind of system. Although, I should say, you see similar bubble formations in fluid flows that are constrained to small lamella, essentially. So that's not necessarily the thing. But the other thing that's, of course, interesting is when you look at the fluid dynamics, you do have some mass conservation, which we clearly don't have. You know, you can change the amount of up or down magnetization arbitrarily. So that I think is the bigger thing that gives rise to real qualitative systems.
I think I would like to